Um, so I guess to begin, where is the Indo-Gangetic Plain? So it's positioned just here, represented by this sort of pink blob, which is just in front of the Himalayan mountain range. So in terms of how old it is, it's actually the Himalayan mountain range and fallen basin is actually a really sort of young feature on the Earth's surface. It hasn't really been around for that long. So it began to form about 50 million years ago when the Indian plates began to collide with Eurasia. And then due to the sort of tectonic loading on the Eurasia continental margin and the ongoing subsidence of the Indian plate underneath the Eurasian plate, we got some localized basin subsidence here in front of the Himalayan mountains, forming this lovely flat region, well, now flat crystal sediments, known as the Himalayan fallen basin and also the Indo-Gangetic Plains. So since the formation of the Himalayan mountains, the mountains have really been dissected by numerous rivers. So they vary in size and in form. So you have these really large Himalayan river systems, which are known as like mountain-fed river systems. So we have the ones like the Yamuna, the Ganga, the Sharda, the Kanali, the Gandak, and the Kosi. And interspersed in between these really large mountain-fed rivers, we have these smaller foothill-fed rivers, which you can just see down here. So as I said, since the mountains formed 50 million years ago, all of these rivers have been sort of incising these mountains, picking up all the sediment and sort of carrying it through the catchment and depositing it into the plains. So I guess where does all this sediment come from? Like I just mentioned, the Himalayan region is very much tectonically active. So I guess a famous example of this would be the Gorkha earthquake back in 2014, and this sort of study here by Roback et al. 2018 sort of shows the dispersal really of all these landslides in the region. And I think another study said that within like a 25,000 kilometers squared area, over 21,000 landslides occurred. So you can imagine all this abundant sediment sort of leaving the hill slopes and entering these channels during these sort of events. And then we can combine these earthquakes and landslides and other sort of climatic causes of potential sediment sources in the region. So the region is very much still glaciated. So within the sort of Teppan Himalaya up here and the greater and lesser Himalayan regions, we still have a lot of glacial cover. So we get a lot of glacial erosion processes going on and potentially big events like glacial peak outburst floods, adding sediment to the system. So on top of this as well, the region is also subjected to the Indian summer monsoon. So during this period, the rivers experience 80% of their water and sediment discharge. So you can imagine all the sediment, which is sort of accumulating on the sort of river valleys upstream during all these landslides and just general erosion throughout the year. It's all sort of picked up, lifted in trains, carried through the catchments and dispersed into the plains. So due to all these factors which I've been talking about, the fact that it's very tectonically active, you've got lots of sort of variating climate controls on sort of sediment entering these systems. The Himalayan region does have some of the biggest and highest erosion rates in the world and also some of the highest sediment fluxes. So it's quite an interesting place to try and understand denudation rates and sediment fluxes. And many people have tried to quantify how much sediment is entering these river systems. So one study by Lupker et al. 2012 tried to do this by using cosmogenic beryllium 10 on sand. So what we can see here is the red numbers represent denudation rates, the erosion rate in millimeters per year, and the blue is the equivalent sediment fluxes per year. And as we can see, within individual catchments, so these are sort of repeated sampling years, is that you do get a little bit of year-on-year variation, which may be due to the sort of stochastic nature of sediment entering these channels. However, if you look along strike of the Himalayan mountains, the erosion rates and sort of sediment fluxes don't vary all that much. And any variation which does occur, sort of as the sediment is moved out of the mountains through the plains, down to this sort of delta region near Bangladesh, you get an awful lot of mixing and buffering. So the erosion rates sort of even out to about 1 millimeter per year. So I think that's what we generally take the erosion rate to be in the Himalayan region, which is pretty high. I think it's actually one of the highest in the world. So another study then started looking at, what are the long-term sort of erosion rates in the region, and which is really quite interesting because this region has been subjected to differences in sort of monsoon intensity and glacial cover through time, especially during the Pleistocene. But what they found is actually the erosion rate has been fairly consistent through time. I mean, you do get some big variations, but overall it's still equating to about 1 millimetre per year, and especially during the Pleistocene. Yeah, I thought that was quite interesting. And then, so when we're looking at the sort of coarse bedload flux at the mountains, a couple of studies have had a look at quantifying this, and one was by Lizzie Dingle, who's also a former PhD student at the University of Edinburgh. So she used the sort of, she measured the volumes of sediment trapped between the mountain front and the gravel to sand transition and converted it into a gravel flux. And what's quite interesting is that as we go along the strike of the Himalayan mountain range, these catchments do vary in size, and particularly when we're sort of looking at these big mountain-fed catchments compared to these sort of smaller foothill-fed catchments, which have just been blown up here. So despite the sort of magnitude change in terms of catchment size by order of 2 to 3, we're actually finding that the gravel flux from each of these catchments is actually broadly quite similar, which is quite surprising, as you can see here. So we just have gravel flux, which is represented in the grey, and the red is just per unit catchment area. So when all this gravel and sand does reach the plains, we do see some very interesting sort of sediment sorting patterns and geomorphic features, which I'm now sort of going to talk a little bit about. So one feature which I'm quite keen to talk about is the gravel to sand transition. So this is a geomorphic feature which is globally recognised. So it's seen in rivers in Canada. So I think Lambert and Diti have looked at the Fraser River, studying the gravel sand transition. We also see it in Romania, but in and also in actually some smaller sort of rivers in Scotland. But I guess I'll be sort of talking more specifically about the gravel sand transition which we see in Nepal and India, in the Indo-Gangetic Plain. So essentially what happens is as the river exits the mountain front, it first deposits this coarse load. So it's like its pebbles and its gravels. And as you move, sorry, my clicker keeps as you move further downstream, you get to the gravel sand transition. And beyond this point, the gravel then only deposits sand. And in Nepal, in the Indo-Gangetic Plain in India, this gravel sand transition is also associated with a break in channel gradient and a change in channel morphology. So what you tend to find is above the gravel sand transition, we have these really lovely big braided river systems. You sort of hit the transition, you get a more meandering single thread river. And in terms of grain size change, I think Bill and Radley really have a nice sort of diagram here which sort of displays the changes in grain size as you go through the mountain and to the gravel sand transition and beyond. So as you can see here, the MFT is just the main frontal thrust, which represents the mountain front. So as the rivers first exit the mountain front, you can see a sort of bimodal grain size distribution where we have these really coarse pebbles and some sand. And as you move further downstream, you get to the gravel sand transition. Beyond this sort of coarse bedload component has dropped off, and we're now only seeing sand. So it's a sort of grain size on the x-axis here. And then some also quite interesting observations to do with grain size and sorting in the region. It's also, I guess Lizzie spent quite a lot of time here looking at grain size, is that along strike of the Himalayan foreland, so from east to west, we see differences in the position of the gravel sand transition from the mountain front, and we also see differences in the rate of fining or sediment fining. So what we find is in the East-Gangetic Plain near the Cozy, the gravel sand transition is much closer to the mountain front, and as we go further west towards the Yamuna over here, the gravel sand transition is a lot further away from the mountain front. And then if we were to look at the sediment fining rates in the east, we get higher fining sediment rates than we do in the west. And this is thought to be caused by localized basin subsidence in the region, where we're having a faster subsiding basin in the east than we are in the west. So this is causing more accommodation space to be formed in the east, which means there's more space for gravel to fill up. So it's closer to the mountain front than it is in the west. So I thought those are quite some nice large-scale observations of these river systems in the region. So just to go back to the gravel sand transition, I think a study which I was also involved with was sort of looking at the channel dynamics above and below this transition, which is also quite interesting. So above the gravel sand transition in this sort of gravelly area, we find the channels are quite static. So what we did is we took some OSL samples here and dated them, and you can see the OSL ages sort of came back as quite old, fairly old anyway. So these paleo channels have been inactive for quite a while, and if we were to look at the satellite imagery of this region, the paleo channels are actually pretty static and they don't really move all that much. But if we go below the gravel sand transition, just in this region here, in the sandstone portion of the river, the channel is an awful lot more mobile, just shown by this diagram here. So you can sort of see the channel swinging across the landscape, sort of eroding all the bed and bank material as it goes. So within the Indo-Gangetic Plain, the sort of dynamic nature of the river channel and how it moves isn't just constrained to changes above and below the gravel sand transition. You also get it above the gravel sand transition, which is something which I'm also been quite interested in. So as I just mentioned earlier, we dated some paleo channels here upstream of the gravel sand transition in the gravel portion, and we found that the channels are quite old, and when we looked at satellite imagery, we found that these channels just don't really move, they don't move very much, they're relatively static. So if we then compared this to the cozy catchment, which is further in the east, all these, so this study is by Chakraborty in 2010, all these channels here represent a different time period of when the cozy active channel occupied a different portion of the gravel fan. So the gravel sand transition, the cozy, is just about here, about 10 kilometres from the mountain front. So we can see there's a lot of apex avulsion going on, and it's a lot more active than the canali. So I think these lines first started being dated at 1760, right the way through to 2009, and here's the big 2008 avulsion. So the two systems are very different in terms of how active they are and how mobile they are across the foreland. So I guess I sort of started thinking then, so I thought this is not where the talk sort of moves on to more about my PhD work, is what could maybe control the differences in the way these channels behave. And I started thinking about grain size and grain characteristics of the sort of coarse sediment which is exported onto or into the Indo-Gangetic Plain, and whether there might be some differences between the catchments from east to west. So like I previously maybe I didn't previously mention actually, so I'll mention that now, is that a lot of the sediment which is sort of entered into the channels, especially from the Tethyan and the Greater Lesser Himalayas, quite high up in here. A study by Lizzie found that all this sediment, especially the softer morphologies such as schist, granite and gneiss, is abraded and converted into finer sand sediment before it reaches the Indo-Gangetic Plain. So only really hard morphologies such as quartzite can really survive the transport distance from this high region down to the plains. Or anything which is entering the channel in these sort of frontal regions can survive the sort of transport distance. So this then made me think, well, what is the role on these sort of frontal foothill ranges here, which is formed of squalic fluvial sediments, just here. So just a little bit of information about the squalic succession. So the squalics were deposited during the Miocene. So if we just take this as a sort of cross section of the mountain range in the plains, and the rivers would sort of be coming down the mountain as they are today and depositing the gravel and sand, very similar to the Himalayan rivers that we see today in the plains. And what's happened is because the region is still tectonically active, this sediment which was deposited in the plain has been sort of uplifted and incorporated into the mountain range, forming the squalic foothills. So what happens is now is the rivers sort of pass through the mountain range and they enter the squalic foothills and they pick up and erode all the squalic sediments and recycle it and enter it into the plains. So I guess what do these sort of squalic sediments look like and why am I so interested in them? So the squalic succession is a fluvial megasequence. So it's deposited by rivers which are very similar to those found on the plains today. So in succession, it sort of coarses upwards from siltstones to sandstones to these really coarse conglomerates. which is so this is a picture of what a conglomerate sort of outcrop looks like. So these conglomerates are made of predominantly quartzite, so the 80 to 95% quartzite. They have a really narrow grain size distribution, so they're quite distinctive, and all the pebbles which form the conglomerate are really well rounded. And then in the sort of general context of how much is within each catchment, when I did a bit of mapping, it turns out maybe 1% of the catchment geology of each of the large Himalayan catchments contains about 1% sphalerite conglomerate. So due to the fact that these sphalerite conglomerates are made of quartzite, and we don't get an awful lot of sort of coarse bedload coming from the high Himalayan mountain ranges, it made me think that potentially, you know, these sphalerite conglomerates may contribute quite a large proportion of the overall coarse gravel flux to the plains. So I had to go at calculating the relative proportions of coarse gravel coming from the whole catchment, which is represented here in the grey, and this is just megatons of gravel flux on the y-axis here, and the orange is the contribution of that flux, which is from the upper sphalerite conglomerate. So as you can see, despite them only forming maybe 1% of the catchment geology for each of these catchments, they can actually contribute quite a lot of coarse sediment to these river systems, especially for Canali and the Gandak. So I think they could potentially contribute up between 30 to 100% of the total coarse bedload which enters the plain. And the Cozy River here, just a reference, it doesn't actually have any upper sphalerite conglomerate within its catchment, so that's 0. So to sort of compare and contrast and see if these conglomerates are actually having an impact on changing the characteristics of the coarse sediment entering the plains, I compared and contrast 3 contrasting catchments. So we have the Mohand foothill fed river here. This is just over at Dehradun, which is in India in the northwest. And this catchment is quite small, and it only locally sort of feeds off sphalerite foothills. So all of its coarse bedload is going to be sphalerite conglomerate. Then we have the Canali catchment, which is a really big mountain fed river system, and it has about 1% of sphalerite conglomerate exposed in its catchment. But potentially from those previous gravel flux calculations graph that I just showed you, potentially these conglomerates could contribute between 37 to 100% of the total bedload entering the foreland. And then we have the Cozy River, which doesn't recycle any upper sphalerite conglomerate at all. So that's almost like any of the coarse bedload coming out to the plains here really represents the kind of first generation hinterland single with no sort of sediment recycling happening there. So what I did is I went to each of these catchments. So in the Mohand and the Canali, I spent a bit of time looking at these conglomerates, characterising the grain size and the lithological content of them. And I also sort of sampled gravel bars going down the systems, down to their gravel sand transitions in each of these rivers. And for the Canali River, just to understand, you know, what potentially the bed load may look like without this recycled component, I took a sample just here above the main boundary thrust, which separates the rest of the hinterland to the sphalerite ranges. So I can compare this sample here to these samples down here, which have got a recycled component to it. So I'm just going to go through some of those results now. So what we did find is actually in the catchments which had a very much a large recycled conglomerate component, in terms of the philological content of the gravel bars, they really showed a high proportion of quartzite. So grey is quartzite, and these colours here are the other sort of Himalayan structural units. So we have the Greater Himalaya and Lesser Himalaya, which I've sort of separated the other lithologies that are just nice and schist into. But for now, we're really only interested in the grey quartzite. So for the Mohand, as we'd expect, it's only feeding off the sphalerite frontal foothills. We're seeing around 80% of the pebbles within the gravel bars that I surveyed were quartzite. And with the Canali, so above the MBT, so before the river goes through the sphalerite mountain range, we find the quartzite percentages are in the gravel bars is actually quite low. But then as we've sort of the river begins to flow through the sphalerite frontal ranges, it begins to pick up lots of the recycled conglomerate pebbles potentially, and we're seeing an increase in quartzite as we move downstream. And by the time we get past the main frontal thrust and into the plains, we're seeing very high proportions of quartzite within the gravel bars. The COSY, on the other hand, really doesn't show this. I think at most we get about 40% quartzite within some of the sampled gravel bars. And then grain size. So just to run you through this here, so I took a grain size distribution from the conglomerates of both the Mohand and the Canali, and they're represented by these grey sort of PDFs here. And the coloured PDFs are the gravel bar grain size distributions. So what we find with the Mohand is as we move progressively downstream and past the mountain front here, the MFT, the grain size distribution of the gravel bars begins to converge onto that of the conglomerate grain size distribution, which suggests that the upper spike conglomerate is the main control on the sort of grain size in the gravel bars, as we'd expect. In the Canali, so above the MBT, where there's no recycling happening, we're seeing a very wide grain size distribution. As we move past the MBT through the Slick Hills, we're beginning to see a slight narrowing in the grain size distribution. And when we sort of go past the main frontal thrust, which represents the front of the mountain range, the grain size distribution of the gravel bars begins to converge onto that of the upper Slick conglomerate. And the COSY samples doesn't have quite a clear story. So the grain size distributions really remain quite wide right the way down the system, and they don't ever really fully converge onto the upper Slick conglomerate grain size distribution. So just for reference, I just put the conglomerate grain size distribution, which I sampled from the Canali, just to see if the COSY did converge onto it, but it didn't seem like it did. So another component which I was quite interested in was shape. So I guess shape sort of came about because we were thinking about this recycling process and the nature of, if these quartzites are sort of going into the plains, they're being uplifted, incorporated into the mountain range, and then sort of eroded and carried back through the foreland again, they've probably experienced quite a long or larger travel distances than, say, a quartzite, which is first generation, has just come from the mountains straight onto the plains. So we thought that maybe the recycled component may be more rounder than the other sort of non-recycled quartzites. So this is probably quite a time-consuming part of my fieldwork, separating the morphologies, putting them on top falling and picturing them, and then also post-processing it when I got home to the UK. But as you can see here, so these are two samples of quartzites from gravel bars about 7 kilometres downstream of the mountain front for the Canali and the COSY River. And as you can see, the quartzites in the Canali are significantly more rounder than those of the COSY. And then if I sort of plotted this up into some violin plots to show the shape. So when we get a roundness of 1, this is almost like a perfect spherical shape. And anything below 1, it becomes more angular. So this is what it's sort of showing here. And as you can see, for the Mohand and the Canali, they've got very similar distributions in terms of the pebble population roundness. So the Mohand and the Canali have very rounded pebbles within their gravel bars. The COSY is a bit more of a mixed bag. So we're getting some sort of rounded, but probably more angular sort of pebbles within their gravel bars. I then plotted this as a function of roundness and distance from the mountain front, just to compare the Canali and the COSY systems. So as we can see, in front of the MBT, so when the Canali has received its sort of recycled component, we can see that it has much rounder pebbles than the COSY. So the COSY is a lot more angular. And what I do find quite interesting here as well is above the MBT in this Canali sample. So this is before the Canali has gone through the Slick Hills and picked up these rounded quartzite pebbles. The quartzite pebbles here are quite angular and are actually very similar to that of the COSY samples down here in the plain. So this would suggest that if the Slick foothills didn't exist in front of the Canali catchment, so the river sort of came out right by the MBT, no recycling occurring, actually the quartzites then in the plain would look very similar to to that of the cozy, which may suggest that, you know, between the lithology change, we're getting predominantly quartzite rich gravel bars, you're getting grain size distributions which are very similar to that of the epistolic conglomerate, combined with the sort of shape of pebbles also becoming more rounder in these catchments which have a highest recycled component. It may suggest that actually along strike of the Himalayan mountain range, depending on how much recycled conglomerates a river receives, really influences what the grain size characteristics of the gravel bars are in the plains. So I've just sort of highlighted this with my slightly garish diagram with all the bright colours. So it just really sort of explains what I just said there. So when you get these catchments which are tapping into the upper side conglomerates, they're becoming more quartzite rich, and the pebbles are a lot more rounder, and you're getting more narrow grain size distributions. Whereas if it's a sort of first generation hinterland signal with no recycled component, the grain size distribution is more varied, so it's wider. We're getting more angular class, and we're getting much more varied lithological pebbles. So we're getting a mixture of lithologies in that. And I guess what are the sort of implications of this? So I think earlier work by Comer and Lee, for example, looking at pebble entrainment, they sort of suggested that, you know, rounded, elliptical, sort of imbricated pebbles, so similar to that of what we find in the canali catchment with a higher recycled component, those sort of pebbles are actually more difficult to entrain than, say, angular pebbles like we see in the cozy. So maybe these differences in sort of revulsion processes that we're seeing upstream of the gravel sand transition, it could in part be related to the sort of nature and the characteristics of the grain sizes in the plains. This is something which I'm quite keen to maybe explore a bit further in the future. And then I guess then to sort of complete this sort of section of my talk, before I move on to the next, is I guess I was quite interested in how, you know, how long are these sort of pebbles, these quartzite pebbles, going to be stuck in this recycling conveyor belt? So I just grabbed this satellite imagery here of the Canali River because I thought it was quite interesting. So you can imagine here that the river's coming down, it's eroding into the swallows, it's picking up all these pebbles, all these quartzite pebbles, and they're being deposited into the plains. And you can see here there's some frost that are just beginning to propagate out of the mountain range. So if these continue and continue to uplift, they'll sort of uplift and incorporate these quartzite pebbles back into the mountain range again. So you can imagine these quartzites are in a sort of a never-ending conveyor belt of being sort of deposited in the plains, uplifted and recycled, presumably until the sort of the mountain building process in the region sort of stops. So I guess then this sort of leads nicely on to the next portion of my talk. So I guess what I just sort of said then is, you know, these quartzite pebbles are potentially stuck in this sort of continuous conveyor belts being deposited, uplifted and incorporated back into the mountain range. And we're sort of wondering, well, do any of these quartzite pebbles ever sort of get to leave the proximal foreland? You know, do they ever go beyond the gravel sand transition and don't get incorporated back into the mountain range? So we started looking around the literature, and they can. They do escape the proximal foreland and the sort of proximal gravel to sand transition. So this recent study by Pickering et al. 2019. So this is the Delta region near Bangladesh, and what they've done, they've taken lots of subsurface borehole samples here, and a lot of them have recovered actually these very coarse sort of pebbles quite far out in the distal plains here. So that's about 200 kilometers from the mountain front, and when you bear in mind the current gravel sand transition in this region is maybe 10 to 20 kilometers from the mountain front, these pebbles have really been pushed quite far out into the plains. So I think this was attributed to some sort of glacial lake outburst flood between 30 to 9,000 years ago, which sort of formed a really deep paleo valley here, and which was filled by all this coarse sediment. And similar things have also been seen in the cozy megafan. So this is work done by Raju Sinha from IIT Kanpur. So he also had some borehole data in both the Gandak River and the cozy. I'm just focusing on the cozy here for now. And he found that actually, 10 kilometres downstream, the gravel sand transition in the Cozy is about 10 kilometres from the mountain front. But these pebbles, which are in the core, were located about 40 kilometres from the mountain front. So again, this coarse bed load has been forced quite far into the distal sandy plains. I guess I wanted to explore this a little bit more and understand, how common are these events in stratigraphic records? Are they fairly frequent? Are they not frequent? And what potentially could cause them? So to do this, I studied some swalic successions. So I mentioned swalics a little bit earlier, so I'll just go into a bit more detail here. So the swalic succession, it just forms the frontal foothills here, the Himalaya, just shown here on this geological cross-section. So the swalics were formed by rivers which are very similar to those today, but during the Miocene. And so I guess how the swalic succession relates to the current day sort of geomorphology of the plains, we can see that this sort of lower swalic portion relates to this sort of distal, silty, muddy sections. We tend to find lots of fossils and muds and all this sort of stuff in this lower swalic. And to progress up the sequence to the middle swalic sandstone, this represents this more sort of medial part of the depositional system, where you're getting more sort of medium to coarse sands. And then this upper swalic conglomerate really represents this proximal part of the foreland, where you're getting a lot of coarse sediment deposition of your gravels and your pebbles. So I guess in cross section, this is what it probably looked like. So you have your pebbles deposited very closely to the mountain front, and you get your sandstones and then your siltstones. So I guess what would this sort of event, if the gravels were to be pushed quite far out beyond the gravel sand transition, what would that look like in stratigraphy? So this is what I tried to illustrate here. So this is the gravel sand transition, and what we have here is pulses of gravels being sort of pushed quite far out into the distal sandy plains. So if I was to look at a swalic succession that was maybe from this sort of region, which is just on the sort of gravel to sand transition boundary, it may look something like this. Whereas if I look at this a swalic succession, and particularly the middle swalic sandstone section, and see potentially a sort of an isolated packet of conglomerate sedimentation like this, it may represent something like this in cross section. So that's the sort of thing I was looking out for when I was going out and looking at these formations. So I started looking at some swalic successions in the Dehradun area of northwest India, along the Mohand anticline. So I logged quite a lot of swalic succession, and what I did find is actually two quite prominent episodes of coarse conglomerate sedimentation within this middle swalic sandstone. So like that previous diagram I just showed you, this could potentially represent a sort of a coarse packet of sediment which has been pushed very far out into the distal sandy plains. So just give a little bit of a description about these deposits. So these packets were they were full of sort of quartzite pebbles. They showed very little imbrication, and they're quite largely matrix supported and had these lovely erosive bases to them. And particularly this second one here, what we found is you had some sort of floating pebbles below this erosive contact, very matrix supported. And then the package sort of carried up here into this sort of find quite dramatically into the sandstone. This sandstone is very homogeneous. It didn't really show any sedimentary structures which you usually associate with these sorts of river systems. So when we sort of delved into the sort of literature and sort of thought about, what these deposits may be, we started coming up with sort of hyper-concentrated flow events, where you get this very concentrated deposition of coarse bed load along the base of the river, and then you get this rapid sort of fallout of the sort of finer sediment which is in suspension on top of these coarse packets, creating these deposits. So that's what we sort of thought may have deposited these conglomerate beds. So I did some quick calculations to sort of figure out well, how far are these conglomerate beds, downstream of the sort of gravel sand transition, or the paleo gravel sand transition, I guess, in this case. So I combined the sort of stratigraphic thickness from the upper to middle sphatic contact, which represents the gravel sand transition through time, combined that with sediment accumulation rates and the convergence velocities, and came up with a sort of a rough distance to where these packets may be relative to the gravel sand transition. So that came up between 10 and 25 kilometres downstream of the gravel sand transition. So these sediment packets have been pushed quite far beyond the gravel sand transition, similar to what we've seen in the cozy core, and potentially like that Pickering study where we see these coarse pebbles very far out in the sort of delta regions. So this is just to illustrate really what I meant by how far these packets have been pushed out beyond the gravel sand transition. So when these sediments were being deposited, very similar to today, you'd have a gravel sand transition, and an event has sort of potentially pushed these gravels quite far out, and it's sort of the whole system then retracted back to its normal sedimentation patterns. So I guess then we wanted to sort of think about, obviously these events, they must be quite significant because they're not overly common in the stratigraphic records. So I guess what caused them, what sort of discharges can mobilize bed load very far beyond the gravel sand transition. It must be a fairly hefty discharge, or it might be something else causing these gravels to move because they're not very common. So working with Maggie Creed on this, so Maggie's very good at doing some sort of sediment entrainment modelling. We sort of thought about which different approaches or equations we could use to calculate sort of bed load transport. So we chose the Peter-Miller approach, as these equations sort of yield the median value for all the different bed loads transport equations which we investigated. And what's also quite nice with this is that we can change the coefficient here, which I've just circled in red, to represent different flow states. So if we changed phi to 1, for example, that would be very much under steady flow conditions, and then we can ramp it up all the way up to phi of 8, which would represent sort of an extreme unsteady flow event, such as a dam break or a lake breach. So this is some of the results that we've come with. So this work, I guess, is ongoing and still in progress. We're hoping to submit it quite soon. So what we did is we had the Peter-Miller equations, and we also combined this with sort of varying degrees of sediment concentration. So just bear with me if I talk you through these graphs. So these graphs, what we thought is like we'd try to figure out how long it would take, for example, to transport this coarse bed load 10 kilometres beyond the gravel sand transition, and tried to then see if that fits with the sort of big events which we're already seeing in the plains today. So, for example, the 2014 Canali flood, which had a discharge of 21,000 metres per second, it lasted between 4 to 5 hours. So if we used a coefficient of 1 in the Peter-Miller equation with very low suspended sediment concentrations, we found that actually it took way too long for gravel to be transported 10 kilometres downstream of the mountain front of the gravel sand transition. It would take 140 hours. And if we compare this to a discharge of 21,000 metres per second, which lasts 4 to 5 hours, this is really unrealistic. So we then sort of tried the different coefficients, which obviously represent more extreme events moving down, and also ramped up the sediment concentration. And what we found is using the higher coefficients combined with a higher suspended sediment concentration, we're getting values much closer to what we experience in today's sort of river systems, sort of about 10 hours here. And this then also sort of confirms in a way what we saw in the stratigraphic record, like I spoke about earlier. Looking at these deposits, due to the nature of the gravel bed, the fact that it was very heavily matrix supported, there's no karst imbrication, and then we have these structureless sandstones on top. We thought this might have been a hyper-concentrated flow events. So based on these equations, the fact that we do need quite high sediment concentrations, combined with quite a high coefficient, which may represent a kind of a big stream event, suggests that these deposits in the stratigraphic record may represent something like a glacial lake outburst flood potentially, or a very extreme monsoon season, which has sort of caused a lot of localized landslides, which has increased the sediment concentration in the water column, and which has helped sort of entrain all this coarse sediment and pushed it downstream. So this is what we sort of came up with. And then I guess then to compare this to a sort of return interval, so we can sort of gauge how extreme these events are. So here we've got the return interval against discharge for the Canary River, just so we can compare the events that we've seen in the stratigraphic record. And when we plot the equivalent discharges of our previous results onto here, we can see that these events recorded in stratigraphy, they probably represent between a 200 to 1,000 year event. So they're pretty rare, but they can be pretty big if they happen. And then I guess then, what are the implications of this? If this coarse sediment can be transported downstream beyond the gravel sand transition, this could cause super elevation within the channel, so it displaces more water. So I guess that would be a big implication of one of these events. And I suppose recently, which sort of caught my attention on the news, is that a sort of big event happened in the Melenchi Cola, which is a tributary just off the Cozy catchment, I think. And this really shows a sort of the river here, and it's really bloated and it's very sediment laden. You can see the water's not very clear and it's very dark and dingy. So I guess this is potentially what a sort of a hyper concentrated flow event may look like. And if this could potentially reach the plains and entrain all this coarse gravel and transport it down into the plains past the gravel sand transition, they may produce similar deposits in the foreland today, as we've seen in the stratigraphic rock record. So I guess that's the sort of end of my talk. I guess the conclusions then from the PhD work that I presented is that sediment recycling can greatly influence the characteristics of coarse sediment exported into the foreland, and then extreme hyperconcentrated events have the ability to transport coarse bedload far into the distal sandy plains beyond the gravel sand transition. And well, thank you for having me here.
Thanks, Laura. That was super interesting. I love the pictures as well. Okay, so we already have some questions coming in, so I'll start asking. This is from Todd Elias. He says, "Thank you for a nice talk filled with a large amount of data, exclamation point. Have you noticed in your observations that there are significant tens or hundreds of kilometers differences in the distances of gravel transport from the riverfront correlated with sustained changes in monsoon intensity, e.g. over the Holocene or longer? You gave an example that they can be pushed quite far out, but it wasn't clear how far out and if there were climate rather than extreme weather drivers for this. Thank you."
So I guess this might be referring to the packets that I've seen in my stratigraphy. So I guess we're not entirely sure what sort of forced these pebbles far out beyond the gravel sand transition. I guess that's really quite speculative, and unfortunately we haven't really got any good date constraints on them either, which is a little bit disappointing. But we were thinking that it was sort of like climatically driven in terms of it was during a period of increased monsoon intensity, or potentially sort of a deglaciation event. Maybe these events would be a lot more common in the rock record. They'd be around the same period, but actually because we're seeing these sort of two isolated events, it makes me think that potentially these are sort of one-off extremes rather than a sort of an overall change in the climate of the region, which would potentially probably cause more of these events to be recorded, if I guess that makes sense.
Yeah, totally.
Cool.
Okay, so we have a pause in the question, so I'll go ahead and ask mine. So you're talking about how you think the avulsion and the migration of channels might be linked to grain size and this recycling of the Schwalek Hills conglomerate. Have you thought about how you might investigate that question further? Because that's super interesting. I was wondering if you had any idea.
Yeah, so I guess if I had more time during my PhD and room for another chapter, I definitely would have added it. So I guess we're quite fortunate, and we have got a lot of discharge data for both the Cozy and the Canary catchments in Nepal. So I'd really like to sort of investigate and do some statistics on the discharges coming out of the mountain range, and see if it's, I guess, compare, is it discharge or is it grain size causing these movements in the channel? So if we can correlate the movements of discharge, potentially it's not the grain size causing it, or maybe the grain size is making it easier for the discharge to impact the movement of the channels, I suppose. So that's something which I would be very interested to continue looking at in the future. I guess there's also other sort of things I've need to investigate as well. I guess like geomorphically, some of these catchments are quite different. So some are a little bit more entrenched, some are a little bit more super elevated. Some of these rivers actually, before they go into the plain, they exit on a sort of a dune valley or a piggyback basin, which might have some sort of sediment storage. So there's a lot of internal and external factors which I'd like to investigate to look at this a bit further.
Thanks, that's cool. Okay, Steffi, yeah, do you want to go ahead?
Yeah, I was just about to ask a follow-up question to what Todd kind of started. So if these gravel sand transitions are so much driven by local activities, I was wondering if you map them along the mountain front today, is there great variability because the rivers are probably different in that total discharge amounts, or if you have an outburst flood, it's only locally one of the rivers and not all at once. So kind of, do you see variability along strike?
Yeah, so Lizzie Dingle, I guess a lot of my PhD book builds on some of her work she did during her PhD. So she mapped a lot of the gravel sand transitions of these large Himalayan mountain ranges. And she found there was an east to west variation in distance from the mountain front. So the gravel sand transition is closer in the east than it is in the west. So we think that overall control on the position of the gravel sand transition is actually based on subsidence, as there wasn't much really difference in discharge and the amount of sediment coming out of the mountains. So in general, it's pretty stable because it's controlled by, well, the gravel front is very stable because it's mainly controlled by subsidence in the falling basin. But I guess we don't know at the moment whether a big event could sort of really grab this gravel and push it through, because we haven't observed it yet, and that's quite a difficult thing to observe. But I think from the sort of stratigraphic evidence we have from like Pickering and Sinnoh and some of this work I've been looking at, potentially a big event which could increase the gravel flux and increase the discharge could push this gravel front further, well, temporarily, I guess, further into the plain. If that answered your question, I'm not sure.
Yes, thanks. And I might just go ahead and read the next question from the chat. Yeah. So it's from Sibashish Dash. I hope that was correct. Is there any link between the incision of the Dun valleys and the modern position of the gravel sand transition?
Was that the Dune valleys?
I guess that's what it's, I think that's what it means.
I haven't looked at that. Again, I don't. So the big dune valleys in Nepal, I guess there's Chitwan Dune, which the Gandak flows through. There's the Tenali's got a very small dune, and then there's Dehradun, which is where the Yamuna and Ganga sort of come out of. So they're quite spatially spread out along the front of the foreland, actually, these dune valleys, and it doesn't seem to have an impact on the distance of the gravel front from the mountain front at this moment in time.
Awesome. Okay.
So I'll ask the.
Oh yeah, there you are. Are there new?
I'll ask the next question by Rajiv Sinha, and he's asking if you thought about sediment connectivity issues and its variability through time that could have been responsible for episodic push of gravels into the plains.
Yeah, so I guess this could also relate to that dune question. So you can get localized storage in these dune valleys, which are, so a few of them are quite close to the mountain front within the spike hills. So you do get some sedimentation in the dune valleys. And I guess, you do get periods of incision and aggregation. So that could have caused some localized gravel pulses to sort of push through the dunes and into the plains. But I also imagine, for these dunes to be incised, and for the gravel to be sort of carried from the dunes into the plains, that would probably be controlled by a tectonic or maybe even a climatic event itself. So I'm not sure whether. So I guess it could be a storage thing that they're just picking up more sediment from the dune and transporting it into the plains. But I think for that sediment to be liberated from the dunes, there'll have to be another sort of external forcing, be it tectonic or climatic, for that to occur. So yeah.
Great. Okay, so we have the next question from Jesse Zondervan. He says, hi Laura, do you have any idea what happens to the gravel bedload derived from the headwaters? Does this gravel get deposited earlier than the recycled conglomerates? And in this case, longitudinal sediment transport connectivity is low, or the massive input from the recycled conglomerate could override the signal from the headwater derived bedload.
Yeah, so I think I might have briefly touched on this, although I might not have, can't quite remember now. But so I think some work has shown that a lot of the sediment that's derived from like the high Himalayas, so like the Tethyan, the Greater and Lesser Himalaya, a lot of the sediments actually the kind of softer sediments, so the high grade metamorphics like the schists and the gneisses, and you also have some sort of granites in there. And abrasion experiments by Mikhail et al. And Lizzie Dingle have sort of shown that when this sediment from the high Himalaya is popped into the channels and transported down through the catchment, because these catchments are so big and so large, that actually abrasion really sort of destroys these pebbles, and they don't actually survive the transport distance to the frontal spike foothills and then onto the plains. So it's only really hard morphologies like quartzite which can survive that transport distance. So really what we're seeing is probably, in terms of bedload coming out the front, is mainly the coarse bedload derived from the frontal spike foothills, and anything which is sort of locally derived from the sort of more frontal regions of the Himalayan mountains, so below the Lesser Himalaya. I think that might answer your question there.
And Jesse's just added, but sediment bedload survives in the cozy.
Yeah, so it can survive in the, like I say, it really depends on, I guess, where in the catchment it's derived. So I can't imagine based on abrasion experiments that, for example, probably Greater Himalaya and above, so Greater Tethyan, which is the highest peaks are furthest away from the mountain front, sediment added to the catchment here isn't going to survive a transport distance. Potentially, Lesser Himalaya and below, so Lesser Himalayan mountains and spike foothill ranges, that sort of sediment is going to probably survive a transport distance and make it into the plains. So, in the Canali catchment, for example, we do have a large component of this is cyclosphaeric conglomerates. We probably do have some sediment which is also derived from the lesser Himalayas as well, just not from the Tethyan Greater because the transport distance is too long.
Okay, I think then I go and read the next question from Sanjay Kumar Mandal. Thank you for the nice talk. The sand gravel transition in the older Himalayan fallen basin record is highly diachronous along the Himalaya. Do you have any idea how the convergence partitioning across the Himalaya leading to such diachronous occurrence of SGT?
So I guess it's I guess the frontal sphaeric hills, so when you look at the contact between the middle and upper sphaeric, which represents the gravel sand transition in the paleosystems, is diachronous in nature, so it varies in age across the foreland. And I'm not entirely sure why it does that. So it could be that basin subsidence rates are different across the basin. So the gravel is prograding at different rates. So then the ages where the gravel contact and the sand contact meets, I guess the age will be different then across the basin. But I'm not 100% sure why it's diachronous across the basin. I'm guessing it's to do with gravel progradation rates. So the gravel front slowly converging over the sand bodies as the origins sort of colliding, and the environments are sort of shifting over each other, where you're getting the pebbles progressively sort of moving over the sand or disty plains as it's converging. So it might be something to do with like localized convergence rates, given the diachronous and given the different ages across the basin contact, but I'm not entirely sure what the exact causes are for that.
I would have another technical question for you. At some point during the first half of the talk, you showed this one figure where you measured gravel flux. So there was this gray and this orange curve.
Yeah.
So how did you actually measure gravel flux? Because this is always the big deal. Huh?
Yeah.
How to measure bedload? Yeah,
so I guess this is quite a coarse way of doing it, because it's obviously very tricky, like you said. So the grey was so the sediment flux measured from the whole catchment, so the grey was done by a similar process to Lizzie, where I took the volume of gravel accumulated from the mountain front to the gravel sand transition and converted it into a flux. And then for the upper spike conglomerate, I took the area of conglomerate which is exposed in the catchment and erosion rates, and that then gave me an approximation for bedload percentage, and then that then gave me an approximate of how much conglomerate was coming out of the system for each catchment as well, if that makes sense. So they're quite coarse for first order estimates, which is why I had quite large errors. Like for the Canali and the Gandak, I had like the recycled component could be between 30 to 100% of the bedload. So yeah, it's quite a coarse way to measure gravel flux, but I guess my errors sort of incorporated that.
Okay, great, thanks.
Okay, so I think we don't have any more questions, but I have one more because I missed at the start what your postdoc was about because I was faffing about with Zoom. But what are you working on now?
So it's quite different. So I guess my PhD was very much data driven, going into the Indo-Gangetic Plains, looking at gravel and all that sort of stuff. But I've taken a slightly different approach now. So I'm using some really lovely high resolution DEMs of Philippine rivers, and we've got some time series of this, and we're sort of modelling how flood hazards are changed through time through anthropogenic change, so lots of gravel mining and potentially just how the river naturally sort of changes through time and how the flood hazard changes with that. So that's what I'm currently doing.
Sounds awesome. I look forward to seeing the results from that.
Yeah, if I get my head around the modelling.
Can do it. Okay, great. So if we have no more questions, I can quickly mention that next week will be our last talk in this particular block, and it'll be given by Anne Voigtlander. I don't know if I'm saying that word correct, Steffi. Yeah. And her title is Optimal Stress States for Geomorphologists. So yeah, hopefully see people there next week. And yeah, Felipe has also just put in the chat as well. I want to apologize to Laura and to everybody that we had some issues this morning with the start, and yeah, hopefully that won't happen again. So thank you, everybody. Thank you, Laura. And yeah, we'll look forward to seeing you hopefully next week.
Cool, thank you. Thanks. Bye.